All right, here we go. We're going to walk through this second exploration. This one it probably feels a little mathier than we're used to, but it's really just some slope calculations. It's not too bad. So I'll kind of go through those pieces with you and highlight kind of how to get about them. But again, we're going at this idea of how do we figure out the speed of a galaxy? How do we determine motion? We talked about this briefly, that we have, because things are in motion, these wavelengths get stretched out. That's really the main idea with this. We have our absorption lines for potassium and hydrogen, and then this calcium ion. And we can see that in the laboratory, we have these set values. And then these values here are what we actually measure that's coming in from space, where those absorption lines are. And so it wants you to figure out what these values are, and so to find that shifted wavelength. We have for potassium about 396.9, and then for hydrogen 400.4. All that is when you go up here and you take this low point, or where they have that there, right? That is 396.9, and then that's 400.4. So that's all they're doing. They're just reading the chart to get those values. So then once you have those values, you actually are going to figure out the wavelength, and it gives you those components. And so if you take either one of them, so if I was to take the 400, I've already forgotten the value. I'm going to take the 400.4, I'm going to take the hydrogen, 396.8, and then 400.4. I'm going to take those values. So if I just plug them into our calculation here, so what was measured is 400.4 nanometers minus the 398.6, I think is what it was, nanometers, whatever that value is up top, over 398.6 nanometers times the speed of light, which is 3 times 10 to the 8th meters per second. The nanometers are all going to cancel out. You're going to be left with meters per second, and you should get around that value. So again, it looks scary. The numbers look weird, but it's really not that hard of a calculation to figure out. All right, if we keep moving, this idea of modeling the expansion, you're obviously not going to have to do this, but it talks about what this expansion looks like, how we get those distances, but you don't have to do anything with here because we're not in class. Don't worry about the analysis piece. Just keep on going down to this expansion of space, where we have this Hubble constant, we have the velocity, and then we have the distance, which is the R value. And then it's asking you to kind of think through what this rising bread component is going to look like. And so we have the initial distance, you can measure it, and then we have those descriptions of how this looks. So basically, we use our Pythagorean theorem. You can draw some right triangles. Right, if I look at this and that, so this was 1, 2, 3, 4. This is 1, 2, 3-ish. I want to find the distance between them, which would be that value there. So if I did it as a 4 and a 3, then it's a 3, 4, 5. That'd be 5 units. And then if I do the same thing over on this one, it's not going to work out to be quite as nice. But I do 1, 2, 3, 4, 5, 6. So that's a 6. 1, 2, 3, 4, 5, 5. And then I know that distance, right? That distance there is the square root of 5 squared plus 6 squared, which gives me some value, right, that we're looking at. What we also want to notice is this idea of the wavelength, right? So you can see here the wavelength that is yellow, right, that period is smaller, right? That wavelength is smaller, and then it's been stretched out. This is this idea of this redshift. As it goes apart, that wave between them gets stretched out, and that's where we can start to see this shift between and measure those values. So that's really all it's looking at, right? This idea of whatever you have, you get your values, you see that it gets bigger, and then you see that thing shifts. That wavelength gets stretched out. All right, and then this is again, how these are measured, this idea of the Doppler effect, where we've looked at it in sound and light. It's this idea of motion, right? Where if you have something going away from you, those sound waves are going to feel stretched out, or the light waves. And then that redshift is that we see is because the distance between them is increasing. All right. This one gives, it's a little confusing. I'm not a huge fan of it, but this idea of where these observers are. So observer galaxy A, B, C, and D. You can click through and kind of look at
Observer in Galaxy B.
what it talks about. What they're looking for us is this idea of our point of view, right? Is we seem to be at the center, right? Because we're not in motion, and then this idea that our perspective is based on where we are. Um, so from any point of view, everything appears to kind of move away relative to every other galaxy because space is expanding, right? It's not there's not a single point that is held as a true value, right? Everything is growing. I think if you think back to this picture, let me see if I can find it real quick. If you think about this picture of bread rising, right? Everything is moving, everything is expanding from each other. And so from any given point, everything looks like it's moving further apart. And that is what the Big Bang model is going to state for us. Uh, let's see. And that's really kind of the take home message, this idea that space itself is expanding, that everything is moving away from each other. And that the way that we measure it is with these absorptions, looking at these stretched wavelengths. And depending on how much of a stretch we have, that gives us our velocity. All right. If that stuff doesn't make sense, by all means, feel free to reach out. I'm happy to talk.